So today we will start with the new experiment of your HT lab, that is natural convection. I think this is the fourth experiment what we are doing, and the aim of this experiment is to determine the experimental and theoretical heat transfer coefficient of a vertical tube using its heat by the natural convection. Okay. So to introduce this, let us speak something about the mode of heat transfer and convection and different types of convections. You know that in heat transfer we have three modes of heat transfer. One is conduction, convection and radiation. We have already completed the experiments on conduction where the heat transfer takes place in solid particles. I think we have done around 3 experiments on that, and now we will start with the convection. So here the convection is a mode of heat transfer that takes place because of the difference in the density resulting from the temperature gradient. So here the heat transfer takes place between medium and the air. Thus, in brief, we can say the mode of heat transfer that takes place in fluids is called as convection. So in the convection we have two types of convections. One is natural convection and another one is a forced convection. So what is natural convection and forced convection? I think you already studied the convection topic in your theory classes. So here the natural convection is one in which the flow of air or gases is naturally, there is no any external force that is applied for the flow of air or the heat transfer medium. Forced convection is that where we use some external force for the flow of fluid around the the solid or the heat transfer medium. So here today we will just discuss about the natural experiment on the natural convection. So for in order to do the experiment on this, we have several empirical formulas. That is, one is the Nusselt number, Reshef number, and another one is the Rayleigh's number. By finding out these three numbers, we can easily find the value of heat transfer coefficient. That is theoretical. And another one method is what? To determine the heat transfer coefficient by doing the experiments. So here we have an experimental setup for natural convection, and let us discuss about the experiment now. So in this experiment, the apparatus required are the natural convection setup, which is having a vertical tube, and we have here you can see this is a natural convection apparatus. As we know that natural convection is a mode of heat transfer between the moving fluid and the vertical tube here. Here is the experimental setup. This experimental setup consists of a specimen. Next one, there is an voltmeter, there is an emitter, there is a temperature indicator and a selector switch, there is a main switch, and there is a fuse which acts as a safety device, and there is a thermostat or heat controller which is available to control the voltage that can be applied for the heater. So this is what the basic setup for natural convection. You just see here, this is a vertical tube, and this is a cabin inside which the vertical tube is located. The heat transfer takes place between the air which is flowing inside this tube and the vertical tube. There is a heat loss. Heat is lost, whatever the heat is supplied to the vertical tube, it is lost by it is assumed that it is lost by the convection. And here we have 1, 2, 3, 4, 5, 6, 7 and 8 total thermocouples which will record the temperatures on the vertical tube. So here in this experiment we have 8 thermocouples. You can see this. There is a specimen and hilum cap, and there is a heater coil, and there are 7 plus 1, that is 8 thermocouples. 7 thermocouples are located on the vertical tube, and 8th one will record the temperature of the cooling cabin. So this is what the basic introduction about the natural convection apparatus. So now let us see observations and tabular column that is required for this experiment. So the observations we have, first one is the specimen, and this specimen that is vertical tube is made up of stainless steel. And next is size of specimen. It has an inner diameter of 38 mm, outer diameter of 44, length 500 mm, and the interval is made up of micron. And next is thermocouples. As I told you, there are 8 thermocouples, 7 of the vertical tube and 1 to measure the temperature of the cooling cavity. And next is emitter. It is ranging from 0 to 2 amps, and there is a voltmeter which is ranging from 0 to 270 volts. These are the observations that are required for this experiment. So next, note down the tabular column. So in the tabular column, first is serial number. So that is number of readings 1, 2, 3. You may take around the 1 to 3 set of readings and calculate the heat transfer coefficient. And next, for each reading, you have to calculate the voltage, emitter reading, that is current, and the temperature reading T1, T2, T3, T4, T5, T6, T7, and T8 from the thermocouple readings. So this is the observation and tabular column which is required to carry out this experiment. So these are the formulas that are required or calculations to be done in order to determine the heat transfer coefficient by natural convection. So here the first one is average surface temperature, that is denoted by Ts. And Ts is equal to T1 plus T2 plus T3, T4, T5, T6. It is a summation. It is an average of the 7 temperatures, that is T1 to T7 divided by 7. So next is surrounding ambient temperature. It is denoted by Ta. It is equal to T8. That is the T8, that is the 8th thermocouple reading from the experiment. This can be obtained from this. So by this we can obtain Ts and Ta. So by using Ts and Ta, we can find out the mean temperature, that is denoted by Tm. Tm is equal to Ts plus Ta divided by 2. So here these all data are available in the tabular column, and Ta is also available in the tabular column. By taking Ts and Ta, you can determine the value of Tm. So I think you have no problem to calculate the value of Tm, which is further used to find the Nusselt number, Prandtl number, and Reshef number. So here you can see from the obtained value of Tm, we have to refer the heat transfer data and book, and we have to find the Prandtl number, Cp value, and the thermal conductivity value, and that is kinetic viscosity value from the data and book. By determining this, next we have to determine the value of beta, that is 1 divided by Tm plus 273. I think we all know that the value 273 is added in order to calculate the value in terms of Kelvin. So next is Reshef number. So Lq, B, G, Ts and Ta and V square. These all values are obtained already. L is nothing but the length of the tube. Beta is nothing but the volumetric coefficient of the thermal expansion. D is the acceleration due to gravity. Ts and Ta are the surface and ambient temperatures, and V square is equal to kinetic viscosity. Next is Rayleigh's number. So here next is to determine the Nusselt number. So to determine the Nusselt number, we have one formula H into L divided by K, and another one is Nu is equal to 0.53 into Rayleigh's number is to 1.4 for the value of Rayleigh's number which is less than 10 to the power of 5. Similarly, for 10 less than value between 10 to the power of 5 and 10 to the power of 8, this is the formula 0.56 into Rayleigh's number is to 1.5, and for the value of Rayleigh's number greater than 10 less than 10 to the power of 12 and greater than 10 to the power of 8, it is 0.3 Ra into 1 to the power of 3. So here we determine the Nusselt number, which is theoretical value. By taking this Nusselt number, if you insert it here in this, we can determine the value of heat transfer coefficient, which is the theoretical heat transfer coefficient. H is equal to Nu K by L, which is nothing but the theoretical heat transfer coefficient. So here we are able to determine the theoretical heat transfer coefficient. Now we will go and determine the value of experimental heat transfer coefficient. So here, to determine the experimental heat transfer coefficient, the formula used is QC is equal to HA into Ts minus TL, where H is equal to heat transfer coefficient and Q is a heat loss due to convection. H is equal to heat transfer coefficient and A is equal to area of heat transfer, surface area, and it is temperature difference, that is surface temperature minus the atmospheric temperature. So here A for surface area, A is equal to pi d into L, where d is equal to diameter of the tube and L is equal to length of the tube. So here you can find this, and here the QC, that is heat lost by the convection, is equal to heat that is transferred to the vertical tube through the heater coil, and that Q is equal to V into I, where V is equal to voltmeter reading and I is equal to emitter reading. So here we determine the value of Q in terms of watt. Taking this value of Q and substituting it here, H experiment is equal to Q divided by pi dL into Ps minus Ta. So here we can find the value of H experiment, that is heat transfer coefficient of natural convection by experimental method. So here we can determine the value of H experiment as well as the H theoretical. So just note down the results for each reading, the value of H theoretical and H experiment. So the last is your result table. Here you can see the results are theoretical heat transfer coefficient, that is value of HT, and next is the experimental heat transfer coefficient, that is value of H, which is determined in the serial number 10 as well as serial number 8. So this experiment on natural convection. So here we can see the variations. We have to just compare the variation between experimental and theoretical value. The variation of around 25 to 30% is appreciable. More than that, it has to be rectified. So this completes your natural convection experiment. So now we will discuss. Now we will discuss the procedure for carrying out this natural convection apparatus experiment. So I already briefly discussed with you the natural convection apparatus setup. Here we have a vertical tube which is fitted with the heater coil and which is having the 8 thermocouple fitted with it in a cylindrical cabin. And here there is a mains, selector switch, voltmeter reading, voltmeter indicator, emitter indicator, and a temperature indicator, and here is a dimmer stat. So to start with the experiment, first we have to start with switching on the electrical supply, and then we have to just switch on the mains, and set the dimmer stat reading. Note that the dimmer stat reading should be greater than 80 volts and it should be less than 180 volts. You can set to the any reading between 80 volts and the 180 volts. And so here I am setting the reading for 100 volts. Once I set the reading for 100 volts, automatically there will be change in the voltmeter reading, emitter reading, and the temperature readings. So after setting the dimmer stat, wait for 40 to 45 minutes so that the heat transfer attains a steady state, and you will get the readings, the steady readings, and you can move ahead for the calculation. Now let us wait for 40 to 45 minutes to attain the steady state. Start with it. Now after attaining the steady state, now you can see here we have set the value for 100 volts, and it is showing the voltmeter reading as a 100 volt. It is showing as a 100 volt, and emitter reading is 0.45. And next you have to take the temperature readings. So to take the temperature reading, just refer the selector switch, which has a 8 switches here, T1 to T8. So if your pointer of this selector switch is pointing towards 1, the temperature that is indicated in the indicator is T1. Similarly, we have to take the reading for T2. Similarly for T3, T4, T5, T6, T7, T8. We can take the readings for T1 to T8. Once the temperature is taken, note down the values for voltmeter and ammeter readings. Once all the readings are taken, you can just adjust. Once all the readings for this set of readings are taken, and next we can go for the readings of second readings. So you have to just adjust the dimmer stat by increasing the voltage, say 122. So I will be setting it for 120. So set it for 120. Wait for few minutes so that again the steady state is attained, and again take down the readings for voltmeter, ammeter and the temperatures for 8 select by using the selector switch. You can repeat the same experiment for two or three sets of readings, and you can take the values and do the calculations to determine the value of H, that is heat transfer coefficient for convection. Thank you one and all.